Now we will look at the nonlinear materials, the ferromagnetics. There are three elements that are ferromagnetic: cobalt, nickel, and iron. They are called ferromagnetic because iron is the most common and most dramatic example. Iron atoms have a large magnetic dipole moment because of unpaired electron spin. In regions called domains, adjacent iron atoms will have their magnetic dipole moments aligned. Here is a view of a magnet made out of neodymium, iron, and boron. These rare earth magnets have very large magnetic fields, and they're the type of magnets I often use for the demonstrations in class. What we are viewing here are these domains. Within a given domain, all the magnetic dipole moments are aligned in the same direction. Now there's many more iron atoms in a domain than I'm showing, but assume that each of these arrows represents an iron atom's magnetic dipole moment, and they're all pointing in the same direction. In an adjacent domain, you'll have the same thing. All the magnetic dipole moments of each iron atom are all pointing in the same direction, but this domain will be pointing in a different direction than this domain. We will apply a magnetic field to our ferromagnetic material by placing it in a coil. By adjusting the current, we can adjust the applied magnetic field intensity. The x-axis is going to be our applied magnetic field intensity, and the y-axis is going to be the magnetic flux density field inside our ferromagnetic material. At a given value of applied H, the resulting magnetic flux density field is going to depend on the history of the material. So you see that there's a very nonlinear behavior to the B versus H curve, and that's what we want to now understand. So let's say this is our piece of iron, and here I'm looking at the different domains inside this piece of iron. So inside each of these domains, the iron atoms will all have their magnetic dipole moments pointing in the same direction. So let me put a single arrow inside each of these domains to represent the direction of those magnetic dipole moments. Let's begin with all of our domains randomly oriented, so there's no net magnetic field coming from our piece of iron. This situation would put us at the origin in our B versus H curve, position O here. Now let's start applying a magnetic field intensity in the X direction. So we know that the magnetic dipole moments will experience a torque given by M cross B. So some of these magnetic domains are going to flip because of this torque and point in the X direction. So now we have quite a few of our domains pointing in the X direction, so that we'll have some net magnetic field. So we'd be at this point right here on our B versus H curve. So now let's continue to ramp up the applied external magnetic field and flip more and more of these domains. At this point, we've gotten all the magnetic dipole moments to rotate and point in the X direction, and we're at location P on our B versus H curve. The magnetization is the magnetic dipole moment per unit volume. And that magnetic dipole moment was getting larger and larger as we got more and more of these domains to rotate and point in the X direction. At this point, they have all rotated and pointing in the X direction, so we're at our maximum magnetic dipole moment per unit volume, or the maximum magnetization, which we will refer to as M sub max. So as we were increasing H, M was also increasing, and that's what led to this rapid increase in B versus H. Now at point P, M has saturated, but we can still apply larger values of H, and B will actually keep increasing, but it will be at a very slow rate. So let's rewrite this equation, replacing M with M sat. So this equation for values of applied H greater than H max. So the maximum magnetization occurs when all these magnetic dipole moments are pointing in the x direction, so I will also refer to that as the magnetization has saturated and refer to it as M sub sat. So we can think of our equation for B for H greater than H max as a straight line, because the second term is a constant, so we can think of this like B. H is our value of our horizontal axis, so we can think of it like X, and this mu sub 0 is the slope M. So in this region, the B field is described by this equation right here. So the value of B along this segment will increase with H with the slope mu sub 0. And for the scale of the B axis, this is imperceptible. In free space, B is equal to mu 0 H. So plotting B versus H in free space will be a straight line with the slope mu sub 0. If I was actually plotting B equals mu 0 H on this plot here, the values of B would be so small that we would not be able to distinguish it from the x-axis. And the slope of this region of our B versus H curve for our ferromagnetic material has the same slope as the free space B equals mu 0 H curve. And if I were to plot the B versus H curve for a diamagnetic material, remember the relative permeabilities are near 1 but a little bit less, then the curve would fall underneath the free space B versus H curve. And if I were to plot the B versus H curve for a paramagnetic material, remember mu sub r for a paramagnetic material is close to 1 but slightly larger. So the B versus H curve will fall just a little bit above the free space B versus H curve. Let's go back to point P, and now let's start decreasing the applied magnetic field intensity. What we would observe is that the magnetic flux density field would start to decrease, but at a slower rate than it was increasing. So that when you got back to no applied external magnetic field, the magnetization will not have returned to 0. So you'd have some residual magnetic field designated as B sub r. So what happened as you decrease the applied field is that some of these magnetic domains would have flipped to some random orientation. So at this point, B sub r, we have some net magnetization in the x direction. And so we've actually created a magnet with the right-hand side being the North Pole and the left-hand side being the South Pole. We will now reverse the direction of the current flowing in our solenoid and start applying a magnetic field intensity in the minus x direction to our ferromagnetic material. When we've gotten to point minus HC, we have half the domains pointing to the right and half the domains pointing to the left, so there's 0 net magnetic field coming from our piece of ferromagnetic material. As we continue to increase the applied magnetic field pointing in the minus x direction, we're going to get more and more of these magnetic dipole moments to flip to point in the minus x direction. When we get to point Q, all the domains will have rotated to be pointing in the minus x direction. Now if we return our applied external magnetic field to 0, we will return along this curve to point minus b sub r. At minus b sub r, some of these domains will have flipped randomly, but will have a residual net magnetic domain moment pointing to the left. So now we will be left with the magnet, but this time the left side is the North Pole and the right side is the South Pole. In this table of relative permeabilities, we see that there are numbers quoted for ferromagnetic materials. We know these materials are nonlinear and cannot be described with this equation. But it is useful to quote relative permeabilities so you get some feel for how different materials compare, and let's explain where these come from. Here we are looking at the first quadrant of our B versus H curve, and this dashed line is the initial curve starting with all of the domains randomly oriented and then applying an external field until you saturate the magnetization. If you find the maximum slope of this line, which is the slope of this solid line right here, and you set it to mu sub 0 mu r, the mu r you determine this way are those values of relative permeabilities quoted for ferromagnetic materials. Let me mention 3 ways you can demagnetize a magnet. The first way is mechanical shock. Dropping a magnet can cause some of the domains to flip to random orientations, decreasing the magnetization or completely eliminating the magnetization. The second one is described in this figure here. We have a magnet, so it has some residual magnetization. We're going to vary the applied magnetic field intensity between negative and positive values, and we're going to continuously be decreasing the amplitude swing of that magnetic field intensity. So that will move us along the B versus H curve like this. And eventually we'll get down to where the internal magnetic flux density field is 0. The third way we can demagnetize a magnet is by heating it. A magnet does not gradually lose its magnetic field with increase in temperature. It happens at a critical temperature called the Curie temperature. This was discovered by Pierre Curie in 1895. If you take a piece of iron and look at its hysteresis curve, it won't vary as you raise the temperature from, say, around room temperature, 23 degrees centigrade, all the way up to 770 degrees centigrade. Then abruptly, with further increase in temperature, you completely lose the hysteresis curve. Here is a picture of Pierre Curie. Because women couldn't attend college in Poland, Maria Sklodowska went to France to attend college. She attended the University of Paris and was known as Marie instead of Maria. Marie was looking for some large laboratory space to do some of her studies, and Pierre Curie had such space and allowed her to use it. Pierre became interested in what Marie was researching, and he also became interested in Marie as they later were married. In 1903, Pierre and Marie Curie received the Nobel Prize in Physics for their research on radiation. Marie was the first woman to win a Nobel Prize. Tragically, Pierre was killed shortly after in 1906 when he was run over by a horse-drawn cart on the streets of Paris. In 1911, Marie would win a second Nobel Prize, this time in chemistry, and their daughter Irene also would win a Nobel Prize in 1935, also in chemistry. Pierre and Marie's notebooks still have to be kept in lead boxes because they are so radioactive. In the Atlantic Ocean seafloor, there is a ridge where lava is flowing up and pushing the two plates apart. When this lava cools in the presence of the Earth's magnetic field, the iron atoms are torqued such that their magnetic dipole moments all point in the direction of the Earth's magnetic field. What is observed in the floor of the ocean is like a barcode. There are regions where the magnetic field points in one direction and adjacent regions where it points in the other direction. In this 80-million-year-old barcode, there have been 183 polarity reversals, so the Earth's magnetic poles flip on average every 430,000 years.